Okay, so my screen is shared, right?
Yes, it is.
Okay, very good. Okay, so yeah, so I will now talk about basically zero-knowledge proofs and its application. So the applications are to commitments and signatures, and I think this is an area that's just sort of getting started in lattice cryptography, sort of getting started being efficient, being useful. So the talk is kind of an overview of what we've been doing. So this is really recent progress. So this stuff is stuff that's really the works I'll talk about that some of them are really either in submission or just in preparation. So it's right, fairly new. So I will give an overview of what we've been doing, and then Gregor will, the second talk, will give the details of the concrete sort of the key constructions that sort of go into this work. Okay, so I will start with an overview and then go into zero knowledge. So, okay, so now I cannot move the screen. Okay. Okay, right. So lattice problems. I mean, I guess you've heard of both two of them. There's LWE and CIS, right? So, but I don't sort of, as a sort of for practical purposes, I don't like to think of them as two problems. I sort of think of them as one. Right, you just write them as a knapsack problem, and that really encompasses both LWE and CIS. So just think of a matrix A. You're given an integer matrix A and T, integer matrix A and a vector T, and the goal is to find an S with small coefficients so that AS equals T mod Q. Right, so this is a knapsack problem over vectors. So, and this is really both LWE and CIS. So if you've seen CIS, then, so if you haven't seen LWE and CIS, then this is the problem, right? Then don't even care what they are. This is the lattice problem that's whose hardness all things are based on. So if you've seen CIS, well, this is the inhomogeneous version of it. The homogeneous one has T equals 0. And if you haven't seen this before, then why is this like LWE? Well, it's sort of simple, right? Because so now I have AS equals T, but this is equivalent to just multiplying by a special matrix B on both sides. So that one part of A becomes the identity, right? So it's the B is the inverse of some part of A. So then it's equivalent to A concatenated with the identity times S equals this T prime. And then if you want, you can split out the S into S1 and S2. So it becomes A prime times S1 plus S2. So S1 is the secret, S2 is the error. So it's really LWE. So I'm not going to make a distinction between these two for the talk. I will just say this is the knapsack problem, and all sort of practical lattice crypto is based on something of that sort, right? How A is chosen is maybe sometimes different. For n true, it's chosen a different way, but for our intents, this is the problem we're considering. Okay, so now the hardness of it. Let's consider it as a one-way function. Okay, so let's say you're given this A, and the function is f of s is as mod q. And the problem is to find the small s prime, may not be the same as s, just to invert the function so that f of s prime equals t. Right, so how hard is this problem? This is the central problem, so how hard is it? Well, I sort of like to draw this very inexact, I mean, there's ignore the slopes. I mean, just going up means it's harder, going down it's easier, right? So it all depends on the norm of s, right? So if everything else is fixed, the dimension is fixed, then the norm of s is what makes a difference. So if the s is very small in this one-way function, then the function is injected. And this is the LWE problem. Then as s grows, becomes larger, larger, and larger, the problem gets harder, harder, and harder, until the point where kind of a times s is an onto function. And this is CIS. So basically, and then it becomes easier and easier and easier. So I mean, intuitively, right, if there's no restriction on s, the size of s is really big, then this problem is very easy, right? Just use Gaussian elimination. So, and really the hardness of this knapsack problem looks like this. So at some point it gets harder, 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 the bigger s is, and then it becomes easier. So ideally what we would love to do is to build schemes that are based on the hardest version. This is exactly where it's sort of almost injective, or kind of the domain of s is the same as the domain of the function, as the range of the function. But you can't do it because we have other constraints. So, for example, encryption schemes, you cannot build it based on this a function that's onto, because you won't have correctness. Signature schemes, you can't base it here because they won't have soundness. So you have problems like that. So you cannot always base it on top, but you will end up basing it on one side or the other, maybe even on both, and then it'll be, people say this is LWE and this is CIS, right? But really it's just a knapsack problem. Okay. So, and now knapsack problems are really lattice problems, because if you can find a short vector in an integer lattice with dimension m and determinant q to the n, sort of ignore the determinant part, not important, then you can solve the knapsack problem. So basically, finding a short vector in a lattice of dimension n, or a close vector. Again, I'm not making this distinction here. So this is practical lattice crypto. So almost all of it is done over polynomial rings. So not over the integers, but over rings. So the rings we're working with is the zx mod f of x. So if you've never seen this before, I'll just do a quick example of what this ring is. So it has addition and multiplication, right? So let's do this sample ring z17x mod x to the 4th plus 1. So what this means is that all operations, you have modular reduction mod 17 and also modular reduction x to the 4th plus 1. So all elements in this ring, you can think of their representatives as basically polynomials of degree 3, right? And whose coefficients are integers mod 17. So to add two polynomials, you just coordinate-wise add polynomials. Now, and do reduction mod 17. But to do multiplication, well, it's also the usual polynomial multiplication, but now the degree of the polynomial can become bigger than 4. And then you have to do a reduction mod x to the 4th plus 1. So here's an example. I mean, you can trust me, I don't know if it works. I took it from some very old slides. I think it should still work. Yeah, you multiply these two polynomials, you get something without any reduction, and then you start subtracting off multiple, then you sort of start writing x to the 4th is minus 1, right? And eventually you end up with a polynomial of degree 3, and that's it, right? So something very important is that if you look at the polynomial on top without reduction mod 4 and one on the bottom, reductions mod 4 do not increase x to the 4th plus 1 do not increase the coefficients too much, right? So for some moduli, if it wasn't x to the 4th plus 1, there could be actually an exponential increase modding by this f of x. But for x to the 4th plus 1, there is not. And this is very useful for crypto, right? That for the cryptography, that doing a reduction mod this polynomial f of x does not increase the coefficients too much. Okay. So now instead of defining lattices over Z, you can define them, at least this knapsack problem over Z, you can define it over any other ring. So now let's say this polynomial f of x is some polynomial of degree d. And now instead of a being in Z n by m, it's now in R n by m. And S is in Rm with small coefficients. So not much has changed, except we're multiplying elements in R instead of Z. And we're still doing mod q, right? So now now if we want to sort of think about the hardness of this problem, the hardness of this problem now increases by the dimension of the polynomial, right? So if you want to find solve this knapsack problem, this now becomes as hard as finding a short vector in an integer lattice, so not over the ring anymore, of dimension d times n. So whenever we try to find short vectors, we convert the lattice kind of automatically gets converted to an integer lattice, no matter where it started. I mean, maybe it started as a lattice over some other ring, but as an additive group, it has an equivalent representation over the integers. But now the dimension of it is d times m, and determinant is also bigger by a factor of d in the exponent. So basically, if you see an n by m relation, a knapsack problem over a ring of, defined by a polynomial degree d, then as a lattice problem, its dimension is d times n. Okay. All right. So now this is all sort of old stuff. So why are we using polynomial rings? Well, maybe over more than 10 years ago, we know that there's these reductions that say that, well, if you can solve average case problems, this knapsack problem for random A, you can actually solve worst case problems over some ring Zx mod f of x, right? So the same kind of worst case to average case reduction that we know for cis and LWE exists for cis and LWE over polynomial rings. So the one thing these reductions don't tell us, right, is how should we choose f of x and q, right? Because the hard problem does depend on f of x. So how should they be chosen? And I mean, unfortunately, the reductions don't say anything interesting about f of x. It says they should be reducible. Multiplication mod f of x should not increase coefficients too much, but otherwise there's no guidance. So it definitely is an open question whether some f of x could make the problem easier, right? So far, not much has happened. There's been some interesting work for very large Q that keeps coming out, but so far there's not much, but definitely it's not because we have some sort of a reduction that we haven't been successful in solving short vector problems for different f of x. The reduction doesn't say anything about that, right? So yeah, unfortunately there's nothing there, but the reductions are kind of useful when it comes to picking Q, and the reductions basically say it doesn't matter, right? They work for any Q. And of course, that they are asymptotic reductions, so it's not quite clear as to really the concrete hardness. But again, some people who sort of suspect, oh, maybe for different Q, if the f of x factors a lot mod Q, it becomes easier. But no, there's always these, I don't know, magical defenses built into the algebraic structure that prevents all these attacks. And I myself also was, was suspicious of some Qs, but no, there's really nothing there. You should really, here I really trust the reduction. So as far as my personal opinion, which f of x is hard? I think they're all hard, but I really have no reason to think that, just because there's no cryptanalysis. But in terms of once you pick an f of x, what should the Q be? I think any Q should be okay. So which of them, since the reductions really don't say much what you should do, which do we use in practice? And here, for efficiency, some popular choices are f of x is x to d plus 1. Remember, it has to be irreducible over the integers. So when d is a power of 2, this is an irreducible over the integers polynomial. And q, we choose a q so that x to the d plus 1 has low degree factors. So it's x to the d plus 1 mod q actually splits maybe completely or just factors of small degree. So the reason we do this is because there's this x to the d plus 1 polynomial leads to very small coefficient growth when modding by it. And if it factors, you can have really, really fast operations like multiplication using the number theory transform. So it's like the FFT, but over a finite. So another popular choice, especially in FHE, is x to the d plus 1, and you take d a power of 2, but q is also a power of 2. And here you have least coefficient growth and pretty easy mod q representation and operations. So that's enough, but you cannot use NTT, at least not directly. And otherwise, f of x is cyclotomic, for example, so it doesn't have to be x to the d plus 1, just some other cyclotomic that has many of the same properties as x to the d plus 1. So these are some of the, if you care about efficiency, these are the things that get used most often. Okay. But what if we don't really care about efficiency too much? I mean, so what about algebraic structure, right? So it hasn't really come into play when you consider basic constructions like signatures and encryption. We do want to choose this special f of x, and we do want to choose this q so you can have efficient multiplication, but it's not really super crucial. Right, so I mean, you could have things maybe it'll be twice as slow, but you can use a different f of x and q. Right, so the point is that the algebraic structure of f of x does not really come into play in these constructions. In basic constructions, we don't really use the algebraic structure of f of x. Now, when we move on to something more interesting, like for example hash and sign signatures and trapdoor sampling. So we talks about it on Wednesday. Then you really want, because of the way these efficient algorithms for sampling work, you really want the cyclotomic f of x, where m has very few distinct small factors. So like x to the d plus 1 is very good when d is a power of 2 because it only has one distinct small factor. The q still doesn't matter too much. I mean, verification will be fastest with NTT if you use an IQ that splits the f of x, but again, it really doesn't matter. So in practice, though, you're like anything other than x to the d plus 1 makes the sampling algorithm really complicated. So we did that for one of our NIST submissions, and then people took it out. The other partners took it out, said no, this is way too complicated. So even the second simplest polynomial to use became way too complicated for this algorithm. So here, let's maybe x to the d plus 1 is the right thing to use, but q doesn't matter. Then we move on to fully homomorphic encryption, and that'll be talks on Thursday, Friday. So there you do want the cyclotomic f of x. The q doesn't matter too much, and there are some trade-offs for different qs. And the reason is because your plain text is not really working mod q. Your ring is mod q, but your plain text is mod p, which is smaller than q. And then you want to have many these Chinese remainder slots of f of x mod p. So f of x should split mod p a lot, and then you can have arithmetic operations mod p and things like that. So that's why you want a cyclotomic, so it can split nicely into linear factors mod p. But the q does not matter too much. And then there's zero knowledge proofs and some applications. So that's this talk. And here, at least the way we'll be describing things is you really do want a cyclotomic f of x. So we'll fix f of x to d plus 1. And here you do want a q where this f of x actually splits in a particular way. So, and the reason is very similar to the reason for FHE, because we do want these Chinese remainder slots for arithmetic operations. But also we want further algebraic structure. And some automorphisms will be useful. And sometimes you may not even want to split into linear factors. You may want to have factors that are slightly larger. So I would say here is right now the area where algebraic structure really matters of phi x. Whereas, so here you do want to pick phi x and q. So, the point here is that I feel that if we want something to sort of support the most number of schemes, maybe you do want to sort of concentrate on choosing this f of x being x to the d plus 1 and choosing a q so that this f of x kind of splits, right, sort of tailored to this f of x. If we only cared about encryption and signatures, it wouldn't really matter at all. I would say almost. And this is what's going on in this competition now. People are saying, should we use this f of x, this q, or this f of x, this q? It doesn't matter too much, but it really begins to matter once you move to more complicated constructions. So I think there really is a lot of good reasons to study some particular f of x's and q's.
Okay. So Vadim, a couple of quick questions. So when you said sort of small expansion factor, in other words, multiplication doesn't increase coefficients by very much. When you said that, is that important for security or is it important for correctness?
So it becomes a bit of a cycle, right? So it first becomes important for correctness. And then if you want correctness, now you have to increase your Q, and then it becomes sort of less secure. So then you have to then increase thing to get correctness, so you end up losing efficiency. So
I see.
it's that. So there's always, in lattices, you can always do anything with anything almost, but it always leads to some vicious cycle of increasing this parameter, then you have to increase this parameter, and until at some point,
So you're saying roughly that if I pick any irreducible f of x, and essentially if I don't care about efficiency, concrete efficiency, just polynomial efficiency, I can pick any irreducible f of x and any q, and that should be.
No, I didn't know. I mean, there are some f of x that really, if you mod by this f of x, it can exponentially grow your.
Good. Okay. So any
that f of x you canness use. That's why I didn't write doesn't matter. I wrote doesn't matter much.
Yeah. So any irreducible with a small expansion factor less than 2 to the n maybe should be.
Well, Okay, so there's no reason for you to pick an f of x with such a large thing. I mean, if you want an f
Just
of
for
x
fun.
with a particular algebraic structure, there's many good ones that you can pick. I mean, there's no reason to.
Just for fun, you know.
Yeah, but it's not fun. It's really not fun if you start setting parameters for these. So okay.
So the second question is maybe this is jumping ahead a little bit,
Mm-hmm.
but there are sort of ring independent, you know, in other words,
Yeah, I know.
things. One of which is yours. Are they far from being practical? You know, they at least take one of the two things out of the picture. You still have to worry about the modulus, but not the ring. Are they far from being practical?
Okay, so the modulus, if you're willing to be impractical, you can even less practical. You can get rid of the modulus as well, at least in digital signatures. But anyway,
Right.
but let's yeah. So okay, so that's a good question. So you're talking about these schemes that sort of don't have an f of x, and if you prove something secure mod f of x, secure, this scheme is secure. It's secure for all
Right.
f of x. So it is, schemes are, you know, let's say maybe 5 or 10 times big longer. So my point of view on that, so this is a personal point of view, is that if you're really building those schemes and you want to say, I want to be as secure as x to the n plus 1, I also be as secure as x to the n plus x plus 1, I want to be also be as secure as this, then I think it doesn't make too much sense, because you can just, you know, how many different polynomials do you think are weak, right? If you know, so if you think, you know, you try x to the n plus 1, you try another one, and you say, okay, both of those are weak, then maybe there's something wrong with ring LWE to begin with, right? So it doesn't make sense to say, I want to rely on all of them. Just rely on a couple of them and just concatenate the, you know, work mod x to the n plus 1, work mod another polynomial, and just concatenate those two schemes. It'll be more efficient. On the other hand, it very well could be that ring LWE for every polynomial is easy, right? But there it's hard. So then it's really not relying on ring LWE, it's relying on some other different problem which we haven't really considered, right? So if that's what you're afraid of, if you're afraid of ring LWE for all polynomials, then I would say, yeah, that makes sense. But if you're just not sure which polynomial, then I think it doesn't make too much sense, because you can just choose a few polynomials and concatenate those. Yeah. Okay. So that's my personal opinion.
Okay, thanks.
Mm-hmm. Okay. So now, right. So now the rest of the talk will be about zero-knowledge proofs and applications. So I want to say there's as a word of caution, right? So we have to be very careful, especially when we talk about zero-knowledge proofs. You know, when you claim I have the shortest lattice-based proof, right? That doesn't mean that's a very hard claim to make, because there are generic, like for example, PCP proofs, and you know, for example, this Aurora, or you can choose Ligero, which can prove lattice relations, right? So they can prove generic circuits, or this R1CS problem, and you can embed a lattice problem into them, and they are actually very succinct. So they actually grow logarithmically in the number of inputs. So just because you don't use PCPs, it doesn't mean that you have the shortest proof, right? You may have, you know, there may be a shorter proof using generic methods. So this is like not a problem for things like FHE, because there's no other way to do FHE other than lattices. And so, you know, you can have a very inefficient scheme and still, you know, and still say this is very interesting. But on the other hand, for zero knowledge, you have to be very careful.
Vadim,
yeah.
Question in the same vein from one of the participants: what happens when the algebraic things, where the ideal splits into many small primes, things like that?
Yeah. So no, I would say no. So none of those papers actually, you know, broke the LWE that that is considered. And I actually had a slide on this, but I removed it. So the point is, so the question is the following, right? So let's say we pick a Q, and x to the n plus x to the d plus 1 splits mod Q. So now there's a lot of ideals, or you know, you can always mod by some factor of f of x, and now you end up with a lattice of a smaller dimension. But this is sort of where the magic the algebraic structure comes in, that well, actually, for let's say you just want to reduce it by a factor of by dimension by 2. So you find some factor of degree d over 2, and you want to mod it there. But you can easily prove that every factor of degree d over 2 has norm square root of q, right? So you will reduce the dimension by half, but your coefficients will increase by square root of q, which is quite a lot, right? So it's really unclear if you're making any progress there. So so in that sense, I would say that no, there hasn't been any sort of anything that kind of gets you worried if you set LW, if you instantiate LW correctly. I haven't seen any attacks that sort of make me wary of any key. And there's good reason for that, because there is algebraic structure that is inherent in these rings. All right, so then the question is, okay, so now we have to be careful, we have to compete with PCP proofs. So what can lattices offer right now? So what they can offer is shorter proofs for certain relations. So for example, the PCP-based proofs have a fixed cost, right? So they cannot go below a certain amount. Once they reach that amount, they don't go too much above it, but they cannot go below something, and that's about 100 kilobytes for somewhat acceptable speed. So you can always make it a little slower and make it much little faster and make it bigger, or slower and make it smaller. But let's say 100 kilobytes is a decent, is the right number. It's not moving. Oh, okay. So and also speed. So lattices can offer speed. So lattice schemes are fast. So for example, if you go back to lattice encryption, they are actually, let's say, 5 times faster than the best, even discrete log schemes. So, and the zero-knowledge proofs use the same operation. So on the other hand, PCP schemes are fairly slow. So they could take minutes or seconds, again, depending on the size of the output, to prove lattice relations. So speed and small size is something that lattices can offer in certain cases. So now, in my personal view, again, is for a lattice zero-knowledge proof to be interesting in some way, I think it should be less than 500 kilobytes. And even though that's still bigger than a PCP thing, it's still interesting because maybe there's ways to improve it, or maybe it's very fast, or so it should be there. Preferably, it should be better than PCPs, but at the very least, one should acknowledge the existence of these generic proofs in terms of speed size, right? So just by looking at lattice-based proofs, it's not enough, because there are these generic proofs that and a lot of interesting work has gone into them in the last couple of years to improve them and make them faster and more compact, things like that. So you have to be careful there. All right. So then the question is, okay, so now we know kind of what our goal is. So, but what do we want to prove in zero knowledge, right? So for starters, it would make sense to prove the fundamental one-way function, knowledge of the preimage or fundamental one-way function for lattices is this: you're given this t equals as and s is small. I want to prove knowledge of s, right? It seems like that should be something useful for something, right? So this is the discrete log equivalent. Here is that you have g to the s for some secret s, and I want to prove knowledge of s. And for discrete log, this is very, very simple, right? This is the Schnorr protocol. So, and dating back to the 80s. So let me actually review it, very briefly, because the lattice things are fairly similar. Okay, and we'll be building up on this as we go along. Okay, so here's the Schnorr protocol, very fast. So the prover has a G and a secret S. The verifier has a G and this H, which is G to the S. And the prover wants to prove knowledge of S. So he picks a random Y. He computes G to the Y. He sends it. The verifier picks a C, a challenge C, sends that over. So I'm going fairly fast because I hope most of you have seen this many times. And then the prover computes SC plus Y. So the point of the Y was to hide SC, so it's uniform in ZP. So SC plus Y is also uniform in ZP now. And there's a Z. And the verifier checks that G to the Z is HC times W. So correctness, it just works, right? Because you can rewrite Z as SC plus Y. and you have g to the sc plus y as g to the sc times g to the y. And honest verifier Zeroknowledge, you can create transcripts by generating random c's and z's, and then you set your w to the quotient g to the z over h to the c, because w is deterministic. Once you have 2, the rest is deterministic, and because z and c are uniformly random, this is exactly the same distribution as the honest proof. Okay, so now let's try the same thing. Let's do what does this actually prove? Extract something. So the prover, so the extractor does the following from the prover, or some who either knows G and S or doesn't know G and S, doesn't matter, right? So the extractor first runs the prover once and gets the C, W, C, and Z, and then he rewinds the prover. And because the challenge space is big, and a successful prover should be able to answer more than one distinct challenge. So he answers to the challenge C prime with a Z prime and get another equation, which is G to the Z prime is H to the C prime times W. So you get rid of this W. This is just standard extraction. And you end up with G to the quotient of Z minus Z prime and C minus C prime equals H. And that's the discrete log, right? So you can extract S from a prover who can win the protocol. Okay, so that was discrete Schnorr very fast. So now let's try the same thing with lattices, right? So let's say you have AS equals T, and you want to prove knowledge of S. But here the important thing is that S has small coefficients. All right, so let's try the same zero-knowledge proof. So you have a prover who knows A and S, verifier who knows A and T. Okay, so the prover, he generates a Y, that's the masking part, and outputs A times Y. The verifier chooses some C in the ring, the challenge C. The prover sends S times C plus Y, which is Z. Okay, so the verifier just checks that A times Z equals TC plus W. For correctness, you can see that it works out. So it's even easier to see correctness here, because A times SC plus Y is ASC plus AY, which is TC plus W. Okay, but I mean, one should see quickly that things go wrong very fast with the other properties. For example, Z should have small coefficients. If you look at the verification equation, if you don't require Z to have small coefficients, then it's very easy to find a Z that satisfies AZ equals blah, right? So Z has to have small coefficients, which is not what we needed last time for Schnorr. There Z was arbitrary. Okay, so Z has to have small coefficients. Okay, so how do we make sure Z has small coefficients? Because Z is SC plus Y. Well, S has small coefficients, good, but then C and Y should also have small coefficients. Okay, fine. Y and C should have small coefficients, and the verifier should also check that Z is small. Okay, no problem. But now there's another problem. Now Z equals SC plus Y is not uniform in the ring, and so it may leak information about S. So this is an issue. So of course, one way to solve it is just you can make Y exponentially larger than S times C. So this is called noise drowning, but this is inefficient because the coefficients of everything grow. So sometimes it's unavoidable. So there are some schemes, not zero-knowledge ones, but other ones that really cannot avoid noise drowning. But here it is avoidable, right? So here's a better solution. So use rejection sampling to make the distribution of Z independent of S. Okay, so we can't have Z be uniform, and we don't want Z to leak S. So here is just a quick overview of rejection sampling. I don't really want to go into it in this talk. That's not the point. So forget lattices or anything else. So just probabilities. You have an access to distribution G of X, but you don't want to sample from G of X. You want to sample from F of X. Okay. So I mean, the standard von Neumann way to do it is you figure out what is the maximum value of F of X over G of X for all X in the domain of G, and you let that be M. And then the solution is you sample X from G, and then you output it with probability F of X divided by M times G of X, right? So this probability is less than 1. That's good. And you repeat other one. So that's it. That's how you get distribution F. So it's easy to see that at every try, the probability of getting X is exactly f of X over M, which is the correct scale distribution. Okay, good. So another way to see this is that the output, this f of X, actually hides the original distribution G. Okay, so that's normally you want to use rejection sampling to sample from the distribution. Here, the intuition is you actually want to hide the original distribution. So now you can do the same zero knowledge proof, but now maybe you add rejection sampling to the last part, right? So here the distribution of Z, yeah, depends on S. So this is like the G that we had in the previous example, right? So you have SC plus Y, that somehow depends on S, and that's bad. But so we want to output a distribution that doesn't depend on S. So here's where you pick the distribution that you want. You hope you can get it, and you do rejection sampling to get it, right? So I'm not going to go into it, but there are many ways to do it, right? You can try for a uniform distribution where each coefficient is random between negative R and R. You can aim for a Gaussian distribution, which results in somewhat smaller Z's. Sometimes you can get a bimodal Gaussian distribution, which makes even smaller Z's. So here, I mean, the line of research here was to sort of pick a distribution that we can achieve and try to achieve it with rejection sampling. So, and sort of the best we could do if it's compatible is this bimodal Gaussian. Again, doesn't matter. The point is that we can get a Z to be only, let's say, square root of the dimension bigger than S. Instead of with noise drowning, it would have been exponentially larger than S. So this is useful for to keep the size of the output small. Okay. So, and the extraction. So now the interesting part is extraction. So the rejection sampling, just believe me, it works. It's not very interesting, at least not for the point of this, not for this talk. Okay, so what happens in the extraction? So let's say there's a prover that can win the game. We rewind him, right? Just like before. So we obtain two equations. So we have AZ equals TC plus W and AZ prime equals TC prime plus W. Just like before, we subtract the two, and we end up with A times Z minus Z prime equals T times C minus C prime. Now, in discrete log, we just divided, and we got a pre-image. But here, it does not make too much sense to divide. So here's the reason. I mean, you can divide by C minus C prime, but first, it may not be invertible. And second, even if it is invertible, the quotient may not necessarily be small. So what you wanted to prove is that you know a short pre-image of T, so A times something equals T, but instead you prove something very different. So A times something big equals T, and that's not particularly interesting. So dividing, doing the second step, the dividing does not make too much sense. But the proof of knowledge that we do obtain, which is A times something equals T times something, because both of these somethings do have small coefficients, this is meaningful, right? And this is useful, and we will sort of build on things using it. So we'll call that a relaxed zero knowledge proof. It doesn't quite prove what we want, but it proves something a bit weaker. Okay, so here's what happens. So the prover knows a linear relation AS equals T, but he can only prove knowledge. He cannot prove that he knows S, but he can prove knowledge of a small c and a larger z, such that AZ equals CT. Okay, so this is what we just saw that the Schnorr type protocol gives us. All right, so what is that useful for? Well, this is actually useful for signatures, and this is how Fiat-Shamir signatures get constructed. So the proof intuition is actually quite simple. So suppose the public key is AT, the scheme is zero knowledge, and an adversary, after seeing signatures, can produce a solution AZ equals TC. So we can extract something from the adversary who is a successful signer, this Z and C, so that AZ equals TC. Okay, great. Well, because the public key is A and T and AS equals T, we can substitute AS for T, and we get AZ equals A times SC. And subtracting, you have A times Z minus SC equals 0, which is a solution to cis. So and because S is hidden from the adversary and it's not unique, Z minus SC is not zero. So it's a non-zero solution to this, right? So so this is sort of an example where, okay, even though we didn't really prove what we wanted, that AS equals T, the thing that we did prove is still useful, and we can get digital signatures from it. So okay, so these relaxed zero knowledge proofs are useful, but they're not really useful for other applications. For example, proving that the ciphertext is proper, because proper ciphertext is really AS equals T. T is the ciphertext. If you prove that you know a small s, small z, so that AZ equals some multiple of T, well, that multiple of T is a proper ciphertext, not T, right? So that's not very useful, right? So okay, we can build signatures, but it's not really what we were after. Okay, so but very recently, in the last couple of years, last year or two, it's continuing now, these relaxed proofs have actually led to what we want. So let me go through what the what the plan or what the roadmap was to getting something useful beyond signatures. Okay, so we have these approximate proofs. So given AS equals T, we can prove that AS prime equals TC for not quite S and not quite 1. Okay. And like I showed in the previous slide, this gives you digital signatures. And again, here, it's not good enough to get the best lattice-based signatures, because you can get signatures from hash functions. But they are very short, right? So they're about 3 kilobytes for about 128-bit of security, right? So once you optimize, and the optimizations, a lot of optimizations, so you can get both. Yeah. So this is better than generic constructions. Okay, so that's digital signatures. I would say that's solved. So you could also get commitments. Some work from 2 years ago, you can commit to messages in R, so messengers in the ring, and you can also in zero knowledge prove linear relations between the messages. But the linear relations are over this ring. Okay, so you could do that. That's also good, and this I'll show later. It's very simple. And then what I thought was finally good, we finally got what we wanted using this idea, and also some ideas from that were used in for example, discrete log proofs for zero knowledge. Kind of sort of at the same time, 2 papers appeared that kind of gave almost a very similar intuitive construction for how to get exact proofs. So you have an S. So you use this commitment scheme, and then using this commitment scheme, you can do more stuff, and then you can really prove that AS equals, an S, and that AS equals T. So it's really exactly what we were after. And the output was about 300 kilobytes. I mean, maybe a little more, a little less for a sort of natural instance that we would use LWE encryption. Okay, so that's a good first step. So something is doable. So now, on to the more recent work. So this is something that we've done. Okay, so now before we had you could prove linear proofs for this commitment scheme, but now we can do multiplicative proofs. So we can prove multiplicative relations between committed values. So that's useful. And once you have that, extension of that is now you can get what they called unstructured proofs. So these are, instead of linear proofs being over the ring, over this polynomial ring, now you can actually get linear proofs over the integers for the commitment scheme. So the commitments could be over rings, but you can prove stuff over the coefficients of the rings. So that, and I'll sort of explain why that's interesting. And from that, you can get exact proofs again. And now you've kind of decreased the size. So now instead of 300 kilobytes, it's about 50 kilobytes. So it's a useful thing to have. And then another thing you can do once you have multiplicative proofs on these unstructured proofs is you can do proofs of integer relations. So for example, I mean, we don't really want to prove relations over polynomials. I mean, polynomials are not realistic. I mean, it's not a real life scenario where you commit to 2 polynomials and you prove, that you have their product. But integers does make sense, right? You may want to prove addition of integers or multiplication of integers. And so this is what you can do once you have multiplicative proofs and unstructured proofs. So in this talk, the remainder of this talk, I will go into I'll sort of go into how you can use multiplicative proofs and unstructured proofs and show what they are, and sort of define more precisely what they are, how to do useful things with them, right? And then afterwards, Gregor will actually show the math, the guts of how you build multiplicative proofs and these unstructured proofs. So I guess now is a decent time for questions before I.
So if there are any questions, please write them in the Q&A thing, or if you're a panelist, you can ask them directly. And I think Vadim will take like a 2, 3, 5 minutes break. Do you want to do that?
I don't know if people. I don't know. I can go on. I'm okay.
Okay.
Maybe I'll do something a little bit messy, and then we'll take a break after the mess, because right now there's not much to rest from, I would say. So I guess the goal of the talk is to explain what it is we can prove for commitments and why it's interesting. Okay, so that's what's going to be for the remainder of the talk. All right. So okay, so now I'm going to describe what is this commitment scheme. So it's very simple. It's actually very, very simple. So the idea is the following. You have two matrices A and B. So these are the matrices you use to commit. And then to commit to a message M, any message in our queue, so it doesn't have to be small, you pick a small r, and you multiply your matrix by r, and then you add M to the bottom part. Okay, so at the end, your commitment is TA and TB. So TA is the part that corresponds to A times R, and TB is B times R plus M. All right, so why is this hiding? Well, it's hiding because we assume LWE is hard, or ring LWE is hard, or the knapsack problem is hard, that AB times R is indistinguishable from uniform. Okay, so it's hiding because of that. And now, so what is opening? So to open, you just reveal a small r, right? So, and once you reveal an r, the M is implicitly TB minus BR, right? Because once you reveal an R, the M is completely fixed. Right? If you know TB, B, and R, M is TB minus BR. Okay, so opening is that. So why is it binding? Well, suppose that there are two R's that are valid openings, R and R prime. And so you have AR equals TA equals AR prime. Well, this implies that A times R minus R prime is 0, which is a solution to this. Okay, so it's very, very simple. And I think this is sort of a lattice instantiation of a very old discrete log scheme. But it's very useful for lattice. So the important feature of this is that you can commit to M with any the coefficients don't have to be small. It can be any size coefficients. And this is important. All right. And so, but we want to prove that we know M, right? This is the main use of this commitment scheme, right? Commitment schemes by themselves are not very interesting. If I wanted a commitment scheme, I would just use SHA, right? But I want to prove something about this commitment, prove something, prove that I know the M. All right. So how would the proof of knowledge go? So I want to prove that I know the R that satisfies AR equals TA. Okay, good. So I'm going to use this. So this looks very similar to what we were trying to prove before, and we failed, right? We tried to prove that I know a small preimage, but we could only prove that I know a somewhat small z and a small c, so that AZ equals C times TA, right? This was the Zeroknowledge proof that led to an efficiency matrix. So that's what we can prove. Okay, I mean, that's fine. Let's say we prove that, right? Now, here's where the invertibility of C is going to be important. If C is invertible in our Q, then we can, in R, sorry, there's no RQ, it's just R, write V equals Z over C. So just define V is Z over C. And so what we're able to prove knowledge of is that if we're given AR equals TA, using that protocol from before, we are able to prove a knowledge of V, an arbitrary size V, so it's not small at all, and a small c, with small coefficients, such that A times V equals TA and VC is small. Okay, so if we were able to really prove knowledge of R so that AR equals TA, we would just prove that we know an R so that AR equals TA, and then R is small. But we can't do that. So instead, we prove knowledge of an arbitrary V, arbitrary length V. There's no restriction on its length that satisfies A's V equals TA, which by itself would be easy. But we also prove knowledge that there's a small c so that VC is small. Okay, so together, these two things together actually do prove that we know M. Okay, and here's why. So to open, you reveal V and C. And so the M, as before, is implicitly TB minus BV. Okay, so basically I say, look, the V, the only V that could have been picked is this one. Well, once that's the only V that satisfies AV equals TA, then M is fixed to be TB minus B. Okay. All right. So now we're going to prove binding. Why is this binding? Suppose there are two openings for different V's, right, that lead to different M's. Suppose this is a commitment to different messages, which means that the V's must be different. Okay. Well, this cannot happen. Here's why. Let's go slowly. So if there are two different V's, then AV equals T equals AV prime. And now you multiply both sides by C times C prime. Okay, so we did that. And then we subtract one side from the other to get A times CVC prime minus C prime V prime C equals 0. Okay, and this is a solution to cis. So why is it small and non-zero? Well, so it's easy to see why it's non-zero, because C and C prime are invertible, so you can just divide out by C prime, and V minus V prime, they're different, so that's not zero. Okay, and why are they small? Well, they're small because V times C is small, and V prime times C prime is small. And so they all have, these have small coefficients. Okay, so it is a proof of knowledge. And I'm gonna go right. So now this is, of course, not as good as just being able to prove AR equals TA. And this is sort of, let me explain, by parameter setting. So this is where parameter setting is useful to understand how to set parameters. So recall what we want. We want hiding. And for this, you want AB times R to look random. Okay. And then we also want binding. And there, the binding said, if you can open to two different messages, then you can solve cis. Remember, A times the CVC prime minus C prime V prime C is 0, right? So now, if you just compute how big this this Y is, which I defined to be CVC prime minus C prime V prime C, well, it's about square root of MD times bigger than R. Okay. So, okay, so I guess I have a question that says, if A is chosen by the committer, so no, A is not chosen by the committer, right? So this is very important. A has to be fixed, some public randomness. A definitely cannot be chosen by the committer. Right, so basically hiding depends on the fact that AB times R looks random, and binding depends on the fact that you can't find a Y that's somewhat bigger than R, the solution to cis knapsack. So now if we go back to this picture, right, of hiding and binding, so how do you set your parameters, right? So you want to first set some parameter R. Okay, so right, so Mehdi is asking if both hiding and binding are computational. So they could be, but so what I'm going to show now, that this is not the right way, that wouldn't be the optimal way to set parameters, right? So, sorry, no, they are, sorry. Hiding and binding are both computational. Yes, correct, right, correct. So hiding is, right, dependent on LOE, and binding is cis, so yeah, these are computations. You can set one of them to be statistical, but that wouldn't be the best way to set parameters. Good. Right, so now you have to pick some norm of R. Yeah. So you pick something, and that's going to be somewhere on this curve, right? Maybe you want to pick it to be at the highest point. You want it to be distinguished from hiding to be as hard as possible. But unfortunately, the difference between what you have and what you can prove is about a factor of square root of MD. So the vector is going to be bigger. So the binding is going to become easier. You can also want to make binding as hard as possible, but then hiding is going to be easier. So you have to make use of this hump in the middle, and you want to set hiding and binding to be kind of approximately the same. So that's why hiding should be on the LWE side and then before the hump, and then the binding should be on the cis side after the hump. And as Mehdi said, both of these become computational. If you want one to be statistical, then you end up with an easier to break overall scheme. So if you have to set higher parameters to get the same computational hardness. Okay, so this is kind of where this this gap in what you can prove comes in when setting parameters in things like signature schemes and commitment schemes. Right? For encryption, this kind of it doesn't really make sense. It's not really useful because there everything's injective. For correctness, you need injective. But when you don't, then you kind of have this. You have to understand that there's this hump between LWE and cis, and you set your parameters to be on either side. Okay. All right. So then now invertibility was important, right? So now so because we needed this C to be invertible, because then our commitment scheme was binding only if C was invertible. We really relied on that. So now we have to understand what invertibility in R means. So the point is that it is, so you can set your Q. So this is where setting Q is important. So this is a sufficient but not necessary condition for x to the d plus 1 to split into irreducible factors. So if Q is, some prime that is 2k plus 1 mod 4k, then we know exactly that x to the d plus 1 splits in this particular way into k irreducible factors. Okay, in this way. So like I said, sufficient but not necessary. Okay, so that shows how it splits. And so now if we look at the coefficient representation of any element, in it, addition is coefficient-wise. But in the Chinese remainder representation, or the NTT representation, as I will call it, this representation is basically a mod one of the factors of x to the d plus 1, a mod another factor. So basically k polynomials of degree d over k minus 1. So that's the Chinese remainder representation of the same polynomial a. And so, and this is useful for many, many things, and it's also useful to sort of understand invertibility. And here, addition and multiplication is coefficient-wise. So what this means, because multiplication is coefficient-wise, this immediately means that an element in R is invertible if and only if its entity representation has no zeros. Because if it doesn't have any zeros, then you can always find an inverse, because these polynomials are irreducible, so they sort of induce a field, right? So if there's no zeros, you can always find an inverse you have to just find an inverse for each individual polynomial, and that sort of gives you the inverse to the whole A, right? So an element in R is invertible if and only if its entity representation has no zeros. Okay, so now we want our challenges or our differences of challenges to always be invertible, the things we extract. So how do we do this? Well, there are two ways. One is that you can set your ring so that you can prove that all polynomials with small norms are invertible. So this sort of, you can prove something like this. It's not hard to prove. So basically, if x to the d plus 1 splits into a few irreducible factors, let's say 8 or 16 for normal parameters, then all polynomials with, let's say, with -1, 0, 1 coefficients will be invertible. This depends on Q as well, but something like this. So you can prove something like that. Good. But I want, for reasons I have not yet explained, I want x to the d plus 1 to split a lot, as much as possible. So for people who are familiar with FHE, it's for very similar reasons. It's because I want these slots, right, to do operations. So how can I make it split more? Well, you can actually prove that the probability that a random polynomial in R with -1, 0, 1 coefficient hits any particular NTT value is very small. So they're actually kind of well distributed. So for example, you know, if Q is 2 to the 32 and it splits into polynomials degree 4, that it really is almost 2 to the -128 chance of a small polynomial hitting any element mod that ring. So what this means is that two values in the extraction are unlikely to collide, and the difference will be invertible mod every x to the 4th minus Ri. Okay, so this is using some Fourier techniques, and yeah, so this is better, right? This just says that, hey, look, if it just splits into large enough degrees, then you should be able to, you will not, these challenges are going to be kind of uniform mod the NTT coefficients, and therefore you will not get the difference of challenges to be invertible, to ever be 0, and so therefore the extracted C will be invertible. Okay. So, and this is what we want. Okay, so I guess I could stop now for 5 minutes.
So yeah, so again, now would be a good time for questions if anybody had one. I have a sort of a clarification thing. I mean, when you prove that a random polynomial, small polynomial hits any particular, and then you apply it to things that come out of the extraction, why are these random?
So because well, the challenges are random because we're considering honest verifier zero knowledge, because we really care about the Fiat-Shamir transform of it, and then they really are random.
Okay. All right. Thank you.
Right. So there are some situations where you know, you're not using zero knowledge proofs, and then the adversary can be maybe adversarial in choosing the C's, and then you cannot apply this. But in this situation where really there is the prover himself is controlling the C's, it's okay.
Okay, thank you. So let's take like a 3 minutes break so that Vadim can catch his breath and the rest of us, and continue in a minute.
Wait, Vadim, this is Hotek.
Yeah, I recognize you, yes.
Just follow up on Shai's question on the previous slide. I'm also a little bit confused because the extraction roughly corresponds to soundness, right?
The what? The
extraction corresponds to soundness, maybe. Mm-hmm. So suppose the adversary breaks soundness with probability epsilon, then it's really only answering the challenges correctly on some tiny epsilon fraction of the inputs. Mm-hmm. So it could be that this epsilon fraction is biased on the polynomials that are not invertible, right? Or
yeah, it's not just a hypothetical thing. There really are attacks that could work this way.
I see. So how is it helpful that only the random polynomials have are invertible?
So, okay, so let's forget extraction, right? Let's just say the adversary, he says, look, I'm looking for a particular C, or I'm looking for a particular entity coefficient, I don't know. I want the first entity coefficient to be something, right? And then I can answer, right? But kind of the main what you can prove is that actually C, the first entity coefficient, there is no, any coefficient has at most a 2 to the minus 128 chance of being hit by any C. So the adversary will be waiting, more than 1 over his soundness time for that coefficient.
I see.
But what you're saying is exactly the attack that can happen in real life. That he really can only answer queries that are this particular entity coefficient is this particular value. And then he can cheat on that. So the question is, what are the factors of x to the d plus 1 mod a q that's a power of 2? Yeah, I don't know. You should ask the people who work on. I don't know if Ray's here or anyone. The people who submitted Sabre. This is their scheme, or even the FH. I don't know, FHE. I mean, FHE is done in a similar ring. Maybe Shai, if someone knows what the factors of this look like. So, I mean, I don't know what the answer is, but this is always what this Q was always, to me, I thought was easier to break, but there's really no reason why I should think so. So, but yeah, I always, this is the one that bothered me the most, especially because, for example, if Q is 2, then the LPN problem becomes sub-exponential. But for Q bigger than 2, it's not. So I don't know. It always bothered me, but I don't think I don't know. I wouldn't bet that there's something wrong with it.
Yeah, I don't know that too. I mean, maybe Chris would know, but.
So this is not something that can be proved using one of these ring leftover hash lemma type of.
You're talking about Daniele, about mod the entity coefficients. No, right? Because no, at least I don't see how, because there's no family of functions here, right? It's that x to the 4th minus r, right? It's not a random r. But it's a simple. It's just using Fourier techniques, because if you can think of it as a stochastic process, and then it's sort of quite not hard.
So I think we can continue, right?
Okay. Okay. So now, okay. So what I did before was basically the commitment scheme, and now here are some things you can proving knowledge that I know the message. Okay, great, you know the message, but this is not interesting. No, not too interesting. You actually want to prove that you know that the message satisfies some relations. Okay, so the first thing, and this is easy, proof of knowledge of linear relations. So I have my commitment, ABR plus 0M equals TATB, so it's a commitment. And I want to prove that I know M and that L times M equals U. So U can be public and L is public. L is a matrix of polynomials in R, right? And so I want to prove that I know basically this M and it satisfies LM equals U. Okay, so this is just a linear relation over the ring. So as it turns out, this is quite easy to prove, and it doesn't increase the size of the proof either. So that's fairly nice. The prover does the following, and this is actually almost exactly like just the regular proof, the zero-knowledge proof that we saw before, that was used for, that resulted in a relaxed extraction. But in green, I will sort of point out the things that are different, that you need for this different L, right? The rest actually just proves that I know an R, and the green stuff is particular to the L. Okay, so I basically pick a y, then compute a times y, and also compute l times by. Okay, and I send both of them to the verifier. So I know I said that the proofs do not get bigger, but here there's a WB, but really it doesn't, because in the non-interactive protocol, you don't send this part. These are computed from the other two values. Or if you can think about it, you can send the hash of this, and you can the verifier can check the hash. So it doesn't matter if I send WA and WB; they're never really sent in the actual proof. Okay. So, but for simplicity, let's say they are sent. The verifier does the same thing as before. It sends a challenge, and the prover responds with RC plus Y. Let's see, right? Okay, so without the green stuff, that's the proof of knowledge of M. Okay, so now the verifier checks that Z is small, AZ equals CTA plus WA, and this green part, which is L times BZ equals C times the difference plus WB. So, okay, this is just messy. I don't know, maybe it's not super trivial, because like when I try to reconstruct it myself, it usually takes time, so I always look it up. And I don't think it's that intuitive, I mean, unless you really stare at it for a while. So I'll just go through it quickly. You don't have to really understand it. The point is that all this requires is an extra verification step, right? So it's the same proof as knowledge of M, but there's this green part where you're checking that L times M equals Q, right? So basically when you extract or rewinding, you have AZ, you basically extract something, and you extract something green, you rewrite AV equals T, and then you have L, you also rewrite the other one, L times TB minus BV is U. Well, as we remember before, AV equals, I guess, TA. And TB minus BV is the implicit message M. So LM equals U. Okay, anyway, it doesn't matter if, I mean, this is obviously way too fast, and I don't think it's very instructive to go through what happens. The point is that it can be done, it's a simple proof, and really there's not much to it. So here, we're just kind of adding to our arsenal of things that we can do.
Vadim, a question. The linear relationship is here over the ring mod Q or over the integers?
Over the ring mod Q. Yeah, everything is mod Q.
Okay, thank you.
Over the ring mod Q. Okay. So once you have this, there's still not much you can do. It's not very useful for things. But it can be used to build more stuff. But in this, right, a note with just one extra commitment, you can be secret to. Here, I assume it was public, but you can make it secret as well. Okay, and this is going to be really what Gregor talks about in the next talk, how to build these more powerful proofs. And I will just explain how to use this linear proof together with these powerful proofs to build some very useful things. Okay, so here are the more powerful proofs that sort of are not linear, we didn't know how to do. So let's say you have commitments to M1, M2, M3, and you want to prove that M1 times M2 equals M3. So this is a multiplicative relation. Okay. Intuitively, this is obviously very useful because, you know, if you want circuits, they have addition, they also have multiplication, right? So you want to prove multiplication. Okay. Now the other one is kind of maybe more interesting. So let's say you're given a commitment to M and N. So polynomials M in the ring and N in the ring. And I'm just going to write them as M0 plus M1x plus all the way up to MD minus 1x to D minus 1. And a public matrix in ZQ D by D. And so what you want to prove, and maybe it seems a little weird right now, you know, why would you want to prove? But actually you can prove that L times the coefficients of M are the coefficients of N. So you can kind of prove that, yeah, some sort of linear relation over the coefficient of the polynomial. So this is very, very different than what we could prove before with linear relations, because here before the linear relation was over the ring. Here it's over ZQ and it's proving some relation over the coefficients of the polynomial. But it turns out that this is very useful. So now for the rest, I will show how to use these three things: multiplicative relations, these proof of unstructured relations, and the linear relation to do some interesting in practice, maybe.
So the linear relation was a special case of this unstructured thing, right? The unstructured thing is strictly wider.
Yeah, exactly. But the proof for the linear relation is more efficient. It's slightly more efficient. Yeah, but yeah, good. Okay, so here's building up from from not very interesting to interesting. All right. So let's say I want to commit to a message with 0, 1 coefficients. Okay, and I want to prove to you that what I committed to actually has 0, 1 coefficients. Okay, so let M. So and the coefficients are going to be in the entity. Okay, so in the entity I have 0, 1. Okay, so now let the message in the ring be such that its Chinese remainder entity coefficients are 0, 1 integers. So then I commit to M, right? So using the usual commitment, right? You have a TA, TB. And now once somebody has TA and TB, they can themselves create a commitment to M minus 1 just by subtracting 1 from the TB part, right? Because remember, TB is just B times R plus M. So if you subtract 1, well, that's a commitment to M minus 1. Okay, great. And now what you want to prove is the product of the committed messages of C0 and C1 is 0. Because if you prove that, that means that you've proved that the entity coefficients, which are, let's say, M1 through MK and M1 minus 1, M2 minus 1, MK minus 1 are 0. And the only way this can happen is if all the MI are either 0 or 1. So this is kind of a standard trick for proving something 0, 1, but you have to get things into that form. Okay, so this was easy, right? So all we did was we wanted to prove that the message has 0, 1 entity coefficients. So we used our product proof to prove that the product is 0. And that implies that the message must have 0, 1 coefficients. Okay, good. So that's one. This, not very far from it, is a range proof, right? We want to show that an integer in binary is between 0 and 2 to the j. Well, again, let's write M in our Q in entity form as MK, M2 up to M1, right? So its binary coefficients are these. So this is almost the same as the previous proof. So now you have a commitment to this. And now you can create a commitment that has 1 in the coefficients. Basically, subtract off 1 if those coefficients can be either 0 or 1. And you subtract 0 if those coefficients really have to be 0. And then you prove that the product of these two commitments is 0. So what that means is that the top part can be 0 or 1, but the bottom part must be 0, right? Which means the high coefficients must be 0, and the low coefficients are 0 or 1, which is a range proof. Okay, so again, this is not surprising. Multiplicative proofs lead to range proofs. Okay, good.
Vadim, sorry.
Yes.
Sorry to slow you down, but you're going very fast. Can you go back to the previous slide for 1 second?
Yeah.
Okay, so what did you prove here? You proved that the M was either 0 or 1?
No. So I didn't prove that the M was 0 or 1. I proved that all of its NTT coefficients were either 0 or 1.
Okay, yes, I understand. That's what I meant. You mean the bits.
Of the entity coefficients, right?
Yes.
Mm-hmm.
Okay.
Right. So it doesn't matter if the entity is, if it's what sort of field it is. I just proved that it's 0 or 1.
Okay.
So if the entities are integer, if it splits fully, these are integers. It's 0, 1. If it doesn't split fully, it's still 0, 1 in whatever ring the entity.
Okay, and now going back to the next slide, saying you reduce to this case. Good, right? Yes.
So I just proved that some entity coefficients are 0, 1. Others must be 0.
Sure. Good.
Okay. Good. Okay. Still not particularly interesting, but okay, good that there was a pause here because I forgot to say it. This is where you want, this is why I wanted things to split, right? Because we can prove these interesting, for example, range proofs, right? So if there weren't a lot of NTT coefficients, if the polynomial x to the d plus 1 didn't split very much, then there wouldn't be a lot of, you couldn't really embed big numbers into it, right? So, I mean, you could, but if it splits a lot, then you can embed big numbers into it. So this is kind of, you want to have a lot of entity coefficients to have a lot of slots to work with. So again, this is very similar to what the FHE people want in their slots. Okay, so now let's go back to the thing that we want to prove, this AS equals T. So how can we use these three multiplicative proofs, linear relation proof, and the other one to prove that AS equals T? Okay, so here's how it works. So I want to prove that I know an S with 0, 1 coefficients, let's say, satisfying AS equals T. So here's what I do. First, I commit to S and to a message M whose entity are the coefficients of S. So I want to commit to M whose in entity it's 0, 1. Okay, and those are the coefficients of S. Okay, then I want to prove that M has 0, 1 entity coefficients. Great, so this is easy. What I haven't done yet is proven that M and M really has the entity coefficients of S. I haven't connected them. Okay, then I prove that A times S equals T. Okay, great. So I have some S, AS equals T. I have some M with 0, 1 entity coefficients. What I haven't done yet is prove that S and M are somehow related, right? So if I could prove that S and M are related in this exact way that in 1, then I'm done. Okay, and this is where the unstructured relation proof comes in. So I'm going to prove that S is the entity of M, and so as it happens, entity is a linear relation over ZQ, right? So to this Vandermonde matrix, right? So I make that linear relation, the unstructured relation proof, I make it the Vandermonde matrix, and I prove that S equals the entity of M. So basically, I use the multiplicative proof of linear relation, and the unstructured relation proof to sort of get exactly what we need. Okay. So this is sort of another use of this unstructured relation proof. Like, what can you put into it? Well, you can put the entity matrix into it, and then it kind of proves what we want. It proves basically connection between the coefficient representation, what needs to be small for all these knapsack problems, and the entity representation. This is what we can prove efficiently to be small with multiplicative proofs. Okay, so this entity, this Vandermonde matrix, being able to prove that one is the entity of the other is what converts between these two representations and allows us to have a proof. Okay, so that's another application. So then we can also do integer sums. So now I want to prove that, let's see. We didn't see the entity coefficient proof. We can make everything non-interactive. Yeah, everything can be non-interactive. So this is, I guess Gregor will show all of the proofs in the next talk. So, but yes, absolutely everything is non-interactive. There's never any interaction necessary. We have Vadim. Okay, so now integer sums. Now, so let's say here's what I want, and this is now realistic, right? So we don't really care about lattices. We just want to prove integer addition. So I'm given commitments to integers M1, M2, M3, written in binary. I want to prove that M1 plus M2 equals M3. All right. So let's first look what addition looks like in binary, right? So let's say I'm adding whatever these two numbers are in binary, right? And I will get the result, and there's this carry vector on top, right? So if you're going to do schoolbook addition, that's what it looks like. All right, good. But I'm working with polynomials. I can commit to polynomials. So let's look, what if I write the first number in polynomial form, so natural way, so zeros and ones, and then the second number is polynomials, and then add them together, right? Well, I still get the right answer in the sense that evaluating this at 2 will give me the correct integer, but that's not really binary, right? So whatever M3 is written in is not going to be that polynomial. But what I can do is that I can say, okay, I'm going to write it, I'm going to kind of keep moving it into an equivalent binary form. So, and the way I can do it, I can always subtract or sort of add x minus 2, which corresponds to doing a carry, right? So if I add x minus 2, this is really like a carry. I subtract 2 from the first slot and add it to the second. I can also add x squared minus 2x, right, if I need to do a carry. Or I can add x cubed minus 2x squared, right? So I'm always adding some multiple of x minus 2, and that's the equivalent evaluation at 2. meaning the binary representation stays the same. And so you get something, and you get this, and that's exactly the answer in binary polynomials, right? So now the intuition is, let C be the carry vector. So as polynomials, you can always write M3 equals M1 plus M2 plus X minus 2 times this carry vector, right? Times whatever I needed to transform something with the correct evaluation at 2 into something that has the same evaluation but has coefficient 0, 1. Right? So there is some carry vector which has zeros and ones, which is like that. And then that's it, right? Then we kind of apply our 3 things. So then we commit to this N1, N2, N3, and NC, whose entity coefficients are M1, M2, M3, and C. So we commit to these. We prove that they have 0, 1 coefficients. That's the multiplicative proof. Then we prove that that really they are the entities of the correct MIs. That's the unstructured relation proof. And then we prove that in its coefficient representation, M3 is M1 plus M2 plus X times X plus X minus 2 times C, which is the linear relation proof. So the intuition here is that we want to do operations as polynomials with coefficients, but we want to prove stuff about these coefficients. And in order to prove stuff about these coefficients, we want to move to the entity representation and use the multiplicative proof. And that's what the unstructured relation proof is for. Okay, so that's how you prove integer sums. Now, integer products, there's a wrinkle here. So let's say you want to prove that you have commitments to M1, M2, M3, and you want to prove that M1 times M2 is M3. Now, it's very, very similar, the intuition, right? So you have a carry vector, right, when you do school book multiplication, but it's no longer 0, 1 carry vector, because if you do school book multiplication, you can actually add, you're adding a lot of things together. Okay, but you do it exactly the same. There's a question. Isn't the entity matrix into an extension of a Q? How do you deal with it? Okay, so I'm not sure I understand the question, but are you saying if the polynomial doesn't split completely, then what is the entity matrix? Or yeah, okay, good. So then it becomes messier, but you can define it as an integer, particular integer matrix or a particular form. So this is something that we did, but for now, let's just pretend it splits completely and it's over Zn. But yes, that's a good question. But this is something that, yeah, good. Okay, so right, so you commit to these guys. Then you prove, just as before, that N1, M2, M3 have 0, 1 coefficients. But now C does not have 0, 1 coefficients as before, because the carries can be bigger than 0 and 1. Okay, so C has small coefficients, but not very big, but not 0, 1. So let's kind of bypass it for now. And then the rest is exactly the same. You prove that the entities of NIs are MIs, and then you prove using a linear relation proof, you prove that what you want. Okay. So the only difference here is that C, this carry, does not have small coefficients. Okay, so if you're if you have coefficients, if you're multiplying 32-bit numbers, your coefficients could be, between 0, your carries could be between 0 and 32. Now, what you don't want to do is you don't want to commit to prove large numbers, right? Because these range proofs get harder the bigger the numbers are. So the proof grows logarithmically in the range size, which is bad. So you don't really want to end up proving that my coefficient is between 0 and 32, right? Because the proof becomes much worse. But you don't have to. And this is sort of another application of this unstructured linear relation. So all we need to do, so why do we need to prove that the coefficients are small? Because what you don't want to happen, you don't want to get a reduction mod Q, because that would just screw everything up. Because you're working you're relating polynomial multiplication over Z to binary multiplication. But if there's a reduction mod Q, you're done, right? Now it no longer makes sense. So all you have to do is prove that the coefficients in C are small enough so that there's no reduction mod Q. Okay, so now what we're going to do is a relaxed range proof. We're not going to prove that the coefficients of C are between 0 and 32. We're just going to prove that they're small enough. All right, so now there's a simple lemma that says the following. So suppose you have a vector, an integer vector, and in zk, and another vector in zn. And now you choose u at random, a random matrix with 0, 1 coefficients. Then u times c plus y mod q cannot be smaller than, cannot have norm smaller than half of c. Basically, you cannot multiply a big number by a random matrix and add some, fixed y, any fixed y, to get something small. So basically, in the pictures, it's like this. If I have a c, if I multiply it with a random 0, 1 matrix, and there's a fixed y, it doesn't matter. uc plus y cannot be small if c is big. So basically, if the result is small, c is small. So basically, in other words, if uc plus y is small, then c must be small as well. So now, important notes. So if you're working over a larger ring, the probability does not sort of scale with the d. It really stays at 2 to the minus n. So kind of, if you're working a big ring, still it doesn't work. So you really need, and also taking the coefficients of u larger than 0, 1 also does not help. So you really need this. And so therefore, it's important that the random matrix u is an integer matrix, even if working over a larger ring. But that's exactly what we can prove again with these unconstrained linear relation. Right? So the idea is the following. We have a commitment to c, and we want to prove that it's small. So you create a commitment to y and send it to the verifier. Receive the challenge u from the verifier. You output z equals uc plus y. And here it's important, this is the reason for why you don't want to leak c, right? And u is small here. So you cannot just output u times c. So you use rejection sampling to not leak c. And then you use an unstructured relation proof to show that u times c is really a commitment to z minus y. Right? So there's sort of another way to use this unstructured relation, and you can show if the coefficients of c are like 32, then for rejection sampling, they'll go up to maybe 64 times nk, which is much less than q. So it has sort of nothing to do with q. So no carries. Okay. So basically, with these techniques, with these sort of relaxed zero-knowledge proofs and things you can do, you get fairly practical things. So for example, this is what we already knew, digital signatures, well, public key, which is commitment size, and signature, which is proof size, kind of an analogy, is 1.5 kilobytes, and the signature is 3 kilobytes. That's really to get this relaxed proof that we saw in the very beginning. And then the commitment scheme, if you just want to commit to a message and prove knowledge of it, it's about 6 kilobytes each. If you want to do a range proof, the proof size grows to maybe 7 kilobytes. If you want to do a multiplicative proof, well, now you're committing to more things, so the commitment size grows a little bit, but the proof is still reasonably 15 kilobytes. And if you want to do multiplication, it becomes 20 kilobytes. So, I mean, the caveat is here, these numbers are approximate and could change. This is really ongoing work. But yeah, so I mean, this is definitely below what you can get with PCPs, right? So there is something sort of useful here, and also I wanted to show that these three relations you can prove: linear relation, multiplicative, and unconstrained are quite useful. So maybe they'll be useful for other things. So so I think there's lots of open problems here in terms of practical things, right? So if you improve this commitment scheme, this main commitment scheme, I think you'll end up improving all zero-knowledge proofs a little bit, if this is the best way to get them. So maybe you can improve zero-knowledge proofs without improving these commitments. So I mean, these are just very general questions, not particularly insightful. And you can of course now start applying these zero-knowledge proofs to get more efficient blind signatures, group signatures, all this stuff that zero-knowledge proofs are used for. So now this very hard problem, I think, is to get practical succinct proofs. So kind of really try to compete with PCP. So there are some sublinear proofs, but the noise grows a lot in these lattice things, and there's no bootstrapping type thing. So in terms of getting succinct proofs, where the proof size doesn't increase linearly, this, I don't know. I mean, practical. I mean, you can do it asymptotically. I mean, I don't know how to do it. But practically, I don't think this will beat PCPs. So really new ideas will be required here. I think it's a very interesting area for research. And then, of course, there's this ROM versus QROM. You know, one of the appeal of lattices is that it's quantum secure. But, you know, the proof, they all have this rewinding, right? And the most efficient instantiations are based on ROM. So there's currently there aren't many QROM proofs. Unless, I mean, there are ways to make them secure in the QROM, but it's less efficient. So it's unclear if it's, you know, it's worth it, because, so the question is, can we prove their hardness in the QROM? And there are some recent interesting works. So Mark will talk about something on Tuesday. And I think another question, and this is the question that I guess, you know, reappeared itself, you know, 30 years later, do we really care, right? I mean, this was the question people asked about the ROM before, and then, I don't know, some people showed that maybe it does matter, but then, you know, it seems like it doesn't, and people kind of accept it. But that's another question is, does QROM really matter, right? If we can we produce any natural example where a proof in the ROM ends up being insecure against the quantum attacker? Can we do, you know, does this exist? And that would be very interesting, because that would show that QROM is actually important. But, you know, as of now, there's no example whatsoever where something goes wrong if you don't consider QROM. Okay, so that was it. And there's a question. PCPs can be used on secret shared data. Can we do something similar? So like MPC, or what is the question? So about secret shared data, is it, can we do MPC or something, or with lattice proofs? I mean, I don't know. So the only two examples, I mean, this is very recent work. So the only two examples kind of we had was the natural one, addition and multiplication. I'm sure that you can do other things. I haven't done it yet. Well, one is I don't know what the questions are. So I'm really looking forward to some talks on Friday about MPC and FHE and private information retrieval. Maybe there will be some interesting applications there. And another question is, the commitment scheme is a symmetric encryption based on LWE. So in the proof, the sender knows the message. So the commitment scheme is a symmetric encryption, meaning that you keep R is the secret key and A is, and you always change the A and the B, right? Is that the construction you had in mind? Yeah, okay. We can achieve security just based on LWE without random oracles or transform. So I don't know about these generic transformations. So I have no, I don't know what the implications are of, I mean, but the thing is, the zero knowledge proof uses a random oracle, right? Our zero knowledge proof is in the random oracle model. So
Vadim, I think the answer is yes in the random oracle model, but you can probably do it better with one of these generic transforms, like Vygotsky.
Yeah. I think the question maybe it wasn't obvious that we were using the random oracles in our proofs, but yeah, our non-interactive proofs are definitely only in the random oracle model. So there is a random oracle.
Any more questions? Okay, so thank you very much, Vadim. We'll take a short break and we'll come back at 1:30, I think, I believe.
1:30 is good.
Well, 1:30 New York time, so I guess 10:30 Simon's time. Bye.